Listen to this, a faint hiss like wind that doesn't exist, a rising whistle that bends and falls, then a burst of sharp clicks, as if invisible pebbles are striking metal. People call it the sound of Saturn's rings. It feels otherworldly, unsettling, and alive. And in a way, it is because those tones are the voice of a giant planet speaking through electricity and ice. Space itself is silent. There is no air between the rings for vibrations to carry as sound. So, what are we hearing? We are listening to measurements turned into audio data gathered by a spacecraft and shifted into the range of human hearing. When scientists sonify space, they take real signals, voltages, frequencies, intensities from instruments and map them to pitch and loudness. It is not make-believe music. It is a faithful translation from one language of nature to another. The story begins with Cassini, the explorer that lived in Saturn's neighborhood for 13 years. On board was an instrument with a simple job: to feel the planet's invisible environment. Saturn is wrapped in a magnetic bubble filled with charged particles. Cassini's radio and plasma wave science sensors sense the waves rippling through that bubble, the same way a microphone senses pressure waves in air. Those plasma waves can be sped up or shifted down until your ears can catch them. A low rumble can be slow plasma waves rolling through thin gas. A quick whistle can be electrons spiraling along magnetic field lines. A fluttering hiss can be turbulence where different regions of the magnetosphere meet. And the clicks? During ring crossings, tiny grains of ice and dust, smaller than sand, older than our planet, sometimes peppered the spacecraft. Each grain hit the metal skin and became a brief electric pulse. The instrument felt those pulses like pinpricks. In audio, they turn into a scatter of pops. It is the sound of ancient ice announcing itself one moment at a time. Here's the real twist behind the singing rings. The rings are not vibrating like crystal goblets. The rings are part of a larger circuit. Sunlight knocks electrons off ring particles. Meteoroids strike and create clouds of charged debris. The planet's spinning magnetic field sweeps past, pulling on those charges and guiding them along invisible highways toward the poles. That flow powers radio emissions, drives shimmering auroras, and modulates the very waves Cassini could hear. The rings sing because they shape the flow of charged particles and the radio energy they produce. We are not hearing rocks. We are hearing electric space responding to the rings. Sometimes the song changes key. When the rings rain, when charged water molecules fall from the inner rings into Saturn's upper atmosphere, the ionized gas there responds. The number of free electrons drops in some regions and rises in others. The spectrum of radio waves shifts. Cassini heard those changes. It is as if the ring system clears its throat, and the pitch of the planet's voice slides for a moment before returning to normal. There are darker notes too. Saturn produces a natural radio beacon called Saturn kilometric radiation. It surges with auroras and with storms, waxing and waning as the planet turns. That beacon can wail like a siren, layered with quick sweeps called whistler mode waves, rising chirps that sound like birds at dawn. Cassini also caught the crackle of lightning from giant storms deep in the clouds. These are not theatrical effects. They are fingerprints of magnetic fields, particle energies, and densities stamped onto a soundtrack your ears can parse. Why does this matter? Beyond the chills? Because listening opens a door that pictures alone cannot. In a single minute of sound, you can hear time. You can hear how the environment changes second by second as the spacecraft dives, climbs, and threads the gaps between ringlets. You can hear when a storm turns on, when dust thickens, when the magnetosphere breathes. Sound compresses complexity into something your mind can track without effort. It makes an alien place feel close enough to touch. And when you realize that the eerie audio is not a Hollywood filter, but real behavior particles accelerated to invisible speeds, magnetic fields carving paths through ice, thunderstorms erupting under a planet-wide roof of clouds, the wonderland's deeper. The sounds give Saturn a personality: curious, restless, sometimes angry, often serene. They tell you that the rings are not a frozen ornament. They are active, charged, and intimately connected to the planet they surround. Here is our promise. In this journey, we will decode the voices. We will separate ring-crossing clicks from lightning crackles, auroral hiss from electron chorus. We will show how Cassini turned fields into frequencies, and why the rings can steer the magnetosphere like a vast, icy rudder. By the end, when you hear that whispering wail or that shower of microscopic impacts, you will know exactly what is performing and why it matters. The music of Saturn is real. It does not travel through air. It travels in fields and particles, and we render it into sound so your mind can feel what the instruments measured. Start with an honest baseline. The song of Saturn's rings is not air vibrating anywhere near Saturn. It is electricity and charged gas, measured by a spacecraft, then translated into audio so your brain can grasp it instantly. Cassini flew with antennas and receivers that sensed tiny changes in local electric and magnetic fields. Those changes, voltages, and frequencies are like sheet music written by the planet. To let you hear it, scientists shift the notes into the range of human hearing and scale their loudness to match the instrument's measured power. It is not a movie sound effect. It is a faithful translation from one language of nature to another. So what plays those notes? Space around Saturn is filled with plasma electrons and ions, moving under the pull of the planet's magnetic field. That field forms a vast bubble called the magnetosphere, an invisible cage that traps particles and guides them along looping rails. When the particles sway together, they launch waves in the fields, and those waves carry information. A slow, rumbling pattern can signal denser gas. A bright, sliding whistle can mean electrons are streaming down a field line toward the poles. The pitch, the sweep, the texture, each is a clue. The sharp clicks you hear in many Saturn tracks come from something more direct. During ring plane crossings or passes through dusty lanes, microscopic grains of ice slam into Cassini at extreme speeds. Each impact flashes into a tiny cloud of plasma and a brief electrical spike the antennas can feel. In audio, a spike becomes a pop. A few scattered pops mean a light spray. A rapid crackle means Cassini has driven into thicker dust. The soundtrack doubles as a dust detector, letting you hear the spacecraft's environment change second by second. Another persistent character is the wide, breathy hiss. That hiss is the translated sound of electrons streaming and scattering in the high-latitude regions where auroras live. Charged particles from the outer magnetosphere race inward along magnetic paths and collide with Saturn's upper atmosphere. They paint polar lights and, at the same time, power a natural radio beacon that becomes audible once shifted into our range. Add bursts from deep thunderstorms. Yes, Saturn has lightning, and you get sudden crackles or staccato bursts riding over the hiss. None of it is artificial. It is the magnetosphere speaking in radio. Here is the subtle truth about the rings. They are not a single solid plate that vibrates like a bell. The rings are a disk of countless icy particles, from dust motes to house-sized boulders, orbiting in a tight, rule-bound dance. Sunlight can knock electrons off their surfaces. Meteoroids can sandblast them, making charged gas. The planet's rotating magnetic field sweeps past and tugs on those charges. All of that changes how current flows through the system. The rings, then, sing not by flexing like metal, but by steering the flow of charged particles and shaping the radio waves those particles generate. One striking adjustment is what scientists call ring rain. Material from the inner rings, charged water molecules and nanograins, falls into Saturn's upper atmosphere along magnetic field lines. That rain alters the ionosphere, the thin, electrically active layer at the top of the atmosphere. When conductivity changes there, the power and spectrum of the planet's radio voice shift. Over months and seasons, Cassini heard the balance tilt and brighten or dim as ring rain waxed and waned. It is the system clearing its throat briefly, changing the timbre, then settling again. How do we know the audio is faithful and not just a cool remix? calibration, and cross-checks. Engineers map specific frequency bands to fixed parts of the audible range and keep that mapping constant. They tie loudness to measured power, not to taste. Then teams compare the audio to other instruments. If the clicks surge, the dust counter usually reports more hits. If the hiss strengthens and the upward sweep grows brighter, cameras often show stronger auroras. If a crackle arrives, radio receivers and plasma sensors typically confirm a storm or an injection of fresh particles. The sound aligns with the physics. There is another twist the ear helped reveal. For decades, scientists used Saturn's radio beacon as a clock for the planet's rotation. But Saturn is not a rigid rock. It is a deep ball of gas, and its magnetic field is almost perfectly aligned with its spin. Without a tilted lighthouse, the radio rhythm can drift as seasons change and the solar wind presses harder or softer on the magnetosphere. Cassini showed that the beat of the beacon is not a fixed metronome. It breathes with the planet's environment, and listening made that living clock obvious. Now, what creates the notes? Saturn lives inside a vast magnetic bubble called the magnetosphere. That bubble is filled with plasma, a thin soup of electrons and ions that comes from the solar wind, from geysers on Enceladus, and from the rings themselves. Magnetic field lines act like invisible rails. Charged particles spiral along them, bounce between hemispheres, and sometimes plunge into the upper atmosphere near the poles. When their motion becomes organized, it launches waves in the electric and magnetic fields. Those waves are what the antennas feel. Say, antennas feel. Different wave modes have different voices. Whistler mode waves climb in pitch like birds at dawn because electrons streaming down field lines radiate energy that slides upward in frequency. Chorus emissions arrive in repeating bands, like a choir warming up on stacked notes. Hiss is a broad, breathy wash that often surrounds auroras. Very low frequency waves can sound like slow surf. Higher ones can become bright, sharp chirps. With a little practice, you can identify each type by ear. Dust writes the percussion. Imagine a fleck of ring ice, smaller than a grain of sand, slamming into Cassini at several kilometers per second. In that instant, the grain vaporizes, ionizes, and leaves a tiny, expanding cloud of charged gas. The impact jolts the spacecraft and shakes a brief pulse of current into the antenna system. In audio, that pulse is a pop. A few pops mean the spacecraft grazed a sparse lane. A steady crackle marks a real spray. If the pattern thickens and the pops begin bunching, Cassini is threading a dustier gap where small particles crowd the plane. Lightning on Saturn adds another layer. Deep in the cloud decks, water and ammonia storms build charge until a discharge rips through. A burst of radio energy races outward. Converted to audio, it becomes a rough, bright crack, often repeating in trains as the storm rotates into and out of view. Mission teams nicknamed the strongest packets Saturn electrostatic discharges. Hearing them revealed storms on the night side long before cameras could catch flashes. At the same time, auroral regions near the poles generate powerful radio beacons that wax and wane with space weather. Shifted into audio, these beacons can wail, sweep, and pulse, marking changes in the flow of charged particles. Now to the rings. As electrical players, the particles that make up the rings are not just cold ice. They are active surfaces under sunlight and meteoroid rain. Ultraviolet light can kick electrons free. Micrometeoroid hits can loft grains and vapor into a thin, charged veil. Saturn's rotating magnetic field sweeps past and tries to drag those charges with it. Where the coupling is strong, currents flow along field lines toward the polar regions. Where it is weak, charges slip. This tug-of-war reshapes how energy moves through the magnetosphere. The rings sing, not by vibrating like a bell, but by steering currents and sculpting the radio and plasma waves that Cassini could translate into sound. There is an elegant feedback. The magnetosphere sculpts the rings, and the rings answer back. Charged nanograins leak inward from the inner rings and fall into the planet's upper atmosphere along field lines. a process often called ring rain. Those grains and water molecules change the ionosphere's conductivity. When conductivity changes, the paths for currents shift, which nudges the planet's natural radio beacon. Over months and seasons, Cassini heard the balance brighten or dim as ring rain waxed and waned. How do we keep the translation honest? By locking the rules and cross-checking with other instruments. A given band of measured frequencies always maps to the same audible band, orbit after orbit. Loudness is tied to calibrated power, not taste. Dust pops line up with spikes in the dust counter. Whistler sweeps match magnetic readings that show electrons flowing along specific field lines. Auroral hiss brightens when cameras report stronger polar lights. Even lightning crackles correlate with radio bursts seen by different receivers. The soundtrack is not a remix, it is a readable record. Listen for structure in a typical close pass. It often opens with a breathy bed from background plasma. A thin, rising line appears the classic Whistler, then splits as neighboring field lines come into view. Random clicks pepper the texture. The density of those clicks climbs into a steady crackle. Now you are crossing a dusty lane. The bed deepens as plasma thickens. A jagged burst rides over the top lightning, or a strong packet from a storm hidden by the curve of the planet. The clicks fade as Cassini exits the dust. The bed lightens again. Without any cutaways, you have heard a whole scene unfold. In the next section, we will isolate each main voice, the dust impacts, the auroral hiss, the whistlers and chorus, and the great radio beacon, and tie each one to a simple mental picture you can carry with you. Once those anchors are in place, the soundtrack stops being eerie ambience and becomes a field guide you can read with your ears. Think of this as your pocket field guide to Saturn's soundtrack. 4 main voices carry most of what you hear: dust pops, auroral hiss, whistlers and chorus, and the great radio beacon. Learn these voices once, and every Cassini audio clip becomes readable. Dust impacts are the percussion. Picture sleet on a metal roof, except each pellet is an ice grain moving at several kilometers per second. When a grain hits Cassini, it flashes into a tiny cloud of plasma and kicks an electric pulse into the antennas. In audio, that pulse is a pop. A few widely spaced pops mean the spacecraft is grazing a clean lane. A steady crackle signals a dusty ribbon near the ring plane. If the crackle intensifies, peaks, and then eases, you've likely heard a gap crossing from entry to exit. Auroral hiss is the breathy bed beneath the track. Electrons stream down magnetic field lines toward the poles and scatter, launching waves across a broad range of frequencies. Shifted into our hearing range, that becomes a soft, continuous wash. When the wash swells, polar lights usually brighten. When it thins, the aurora often fades. If the hiss rises and falls in slow pulses, the magnetosphere is probably being squeezed and released by gusts in the solar wind. Whistlers and chorus are the birds. A whistler is a slender tone that glides upward in pitch as electrons spiral along a field line into regions of stronger magnetic field. Chorus arrives as layered sweeps, a flock calling at dawn. At Earth, chorus strengthens when fresh electrons are injected during magnetic storms. Saturn shows similar behavior. In audio, these are the quick, bright signatures that tell you high-energy electrons are on the move. The Great Beacon is Saturn kilometric radiation, the planet's own radio lighthouse. It thrives near the poles, grows and shrinks with particle flows, and in sound can wail, pulse, or beat in slow waves that feel rhythmic. For decades, its period was treated like a reliable clock for Saturn's rotation, but Cassini revealed that the beat drifts with seasons and with solar wind pressure. A changing rhythm is not the planet spinning faster or slower. It is the magnetosphere breathing. Now place the rings inside this quartet. They do not vibrate like a giant bell. They conduct the band. Sunlight knocks electrons off ring particles. Micrometeoroids loft charged dust. Those charges couple sometimes tightly, sometimes loosely to the rotating magnetic field. Where coupling is tight, Currents flow cleanly along field lines to the poles, brightening auroras and strengthening the beacon. Where coupling is weak, charges slip and smear, hiss thins, and the character of the birdsong shifts. The rings sing by steering currents and sculpting waves. Listen for ring rain as a special effect. From the inner rings, charged water molecules and nanograins slide inward along magnetic lines and fall into the upper atmosphere. That rain removes free electrons in some layers and changes conductivity in others, subtly detuning the radio voice. In audio, this can sound like the bed losing warmth or the beacon changing key for a while. The effect can last hours to days and varies over seasons because sunlight and ring geometry change the charging. Lightning adds drama. Deep water ammonia storms build charge until a discharge rips through the clouds. The burst of radio energy, called a Saturn electrostatic discharge, rides over the hiss as a rough, jagged crack. Trains of evenly spaced cracks reveal a long-lived storm rotating in and out of view. Radio hears it on the night side and through thick cloud, so sometimes the crackle arrives before any camera sees a flash. One more player matters. Enceladus, the small ocean world feeding a broad torus of water, group plasma along its orbit. Near that region, the baseline can thicken and the bird song can change, because added particles alter how waves grow. If hiss turns grainy and whistlers grow busy, you may be hearing the plume's fingerprints on a planet-scale soundscape. With these pictures in mind, a track becomes a map. A soft wash with thin birds and no pops says high latitude on a quiet day. Add a few pops and a stronger wash, approaching the ring plane under an active aurora. A sudden spray of clicks that bunch and blur marks a dusty gap. Bright, rising birds stacked in bands point to a fresh injection of electrons. Ragged cracks announce a storm. A slow roll in the beacon's beat over an hour tells you the magnetosphere is responding to changing solar wind. This is the value of listening. Sound is time made intuitive. Your ear separates layers, and senses change with almost no effort. The sonified clips are not decoration, they are fast, honest summaries built from calibrated measurements. In the next section, we will walk through one close Cassini pass, second by second, calling out each voice as it appears and tying each moment to a clear physical cause. Once you can match sound to process, the ring's eerie singing becomes a story you can follow in real time. Imagine you hit play on a 1-minute Cassini clip from a close pass near the ring plane. No cuts, no music. Just the raw, translated environment. In the first few seconds, you hear a thin, airy bed, like distant surf. That is the background plasma, electrons drifting and jostling in Saturn's magnetic field. The bed is not silence, it is the living space around the planet. A faint, rising tone slides through it, then another. Those are whistlers, the quick voices of electrons streaming down magnetic field lines toward the poles. Your ear catches the glide instantly and files it as safe, ordinary weather. 10 seconds in, the texture grows grainier. Random pinpricks begin to pepper the track. Click, 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 dust. Each pop is a microscopic grain of ice, smacking Cassini and flashing into a tiny puff of plasma that the antennas feel as a spike. A dozen pops per second means the spacecraft has entered a thin spray, noticeable, not dangerous. You can practically picture the metal skin ticking under the hits. As the pops thicken, the bed deepens. The wash grows louder and slightly rough, as if wind is picking up. This is auroral hiss strengthening, a sign that field-aligned electrons are flowing more strongly. When auroras brighten near the poles, hiss tends to swell. Your ear hears more light, even though your eyes see only the data. Around the halfway mark, the birds arrive. Layered, bright sweeps chorus stack atop the hiss, like a flock calling at dawn. That means fresh electrons have been injected and are being organized by the magnetic field. In plain words, the magnetosphere is active right now, and Cassini is inside the action. The scene has energy. Then, a brief, ragged crack tears across the soundscape. It is not dust too rough, too broadband. That is lightning, a burst of radio from a deep water ammonia storm rotating on the far side. On the spectrogram view that scientists use, this would appear as a wide, bright stripe. In audio, it is unmistakable. The storm may be hidden from cameras, but the radio makes it loud. Seconds later, the clicks bunch. The shower becomes a sizzle. Cassini is threading a dustier lane near the ring plane. Here the instrument's ears double as a shield monitor. The thicker the sizzle, the more closely engineers watch the hit rate. Still, this is what the mission was designed for, to taste the environment, not just photograph it. The spacecraft keeps flying, and you keep listening. Now something subtler. The overall tone of the bed shifts, just a little thinner, slightly cooler. This is what ring rain can sound like after translation. Charged water molecules and nanograins falling from the inner rings into the planet's upper atmosphere change the ionosphere's conductivity. When that happens, the pathways for current reroute, and the planet's radio voice detunes for a while. If you stack many passes, this color change lines up with geometry. The effect is strongest where inner ring material feeds field lines that thread the equator, and weakest where that coupling is poor. Near the end of the minute, the pops fade. Cassini has crossed the densest part of the lane and is easing out. The chorus thins to single whistles. The hiss softens. The beacon's Saturn kilometric radiation rolls underneath like a slow tide, rising and falling in strength. On some days, the beat drifts. On others, it steadies. Either way, you can tell the system is breathing. What did you just experience? A complete scene told only through sound. Dust meant solid stuff in the spacecraft's path. Hiss and chorus mapped particle flows and auroral activity. A crack marked a storm. A slight detuning hinted at ring rain, altering how currents close through the upper atmosphere. And all of it was timed by the real motion of a real spacecraft, not by an editor's timeline. This way of listening has a surprising bonus. It trains your intuition. After a few clips, you stop translating in your head and start anticipating. When the clicks thicken, you expect the hiss to deepen. When the birds get busy, you listen for a lightning crack. When the bed thins, you wonder if ring rain is in play. You are learning the grammar of an alien weather report. Scientists lean on that intuition too. Sonified data lets a researcher skim hours of recordings quickly and flag minutes worth deeper analysis. A stray pattern, a repeating train of cracks, a sudden high chorus layer jumps out to the ear, then directs the math. Sound is not replacing plots. It is guiding where to look, and it gives the public an honest feel for what the spacecraft lived through. And remember, none of these voices would exist without the rings. They are the quiet conductor. Sunlight charges their grains. Micrometeoroids loft fresh dust. The rotating magnetic field tries to drag the charges along. Where coupling is tight, currents flow cleanly to the poles and the beacon brightens. Where it is loose, hiss thins and the birds change their tune. The rings do not clang like bells. They steer a planet-scale circuit whose music we can finally hear. Hold that map in your mind, because next we will slow down and unpack the why beneath each voice. How does a single grain make a pop you can hear across 1 billion kilometers? Why do whistlers glide up instead of down? What sets the beacon's beat, and why does it drift with seasons? The answers fit on a few simple pictures, and once you have them, Saturn's eerie song stops being a mystery and becomes a conversation you can follow. Let's slow the scene and ask why each voice behaves the way it does. Start with the birds, the whistlers, and the chorus. Electrons spiral along magnetic field lines like runners on a helical track. As they move inward towards stronger magnetic fields, the natural spin frequency for electrons rises. Waves that couple to those electrons can climb in frequency. So, in audio, they glide upward. In other cases, especially when a lightning pulse launches lots of different frequencies that spread out as they travel, the higher notes arrive first, and the tone falls. Cassini heard both rising and falling sweeps. The direction is a clue, It tells you about where the wave was born and how it moved through Saturn's magnetic rails. What sets the strength of that birdsong? Free energy. When a fresh crowd of fast electrons pours into a region, often injected by a disturbance farther out in the magnetosphere, they feed the waves and make them grow. Think of air rushing across a reed to make a clarinet speak. Where the rush is steady and aligned with the field, chorus sounds bright and layered. Where it is weak or scrambled, you get only a thin hiss. Now to the breath underneath the auroral hiss. Picture field lines as invisible rails that connect space to the poles. Electrons slide down those rails into Saturn's upper atmosphere. As they cross regions where density and magnetic strength change, they scatter and spray energy across a wide range of radio frequencies, shifted for our ears. That becomes the soft wash that swells and fades with the auroras. When the solar wind squeezes Saturn's magnetosphere, more electrons are funneled downward, and the wash grows louder. When the pressure eases, the wash thins. The sharp clicks, the dust pops, are mechanical in origin but electrical in detection. When a grain hits at several kilometers per second, the kinetic energy vaporizes a pinch of material into a hot, ionized puff. That puff couples to the spacecraft's skin and antennas, producing a brief spike in voltage. Bigger, faster grains make bigger spikes. A cloud of tiny grains makes a sizzling texture. Because Cassini's antennas were always listening, the instrument doubled as a dust counter without any extra hardware. The denser the pops, the dustier the lane. Lightning adds the jagged edges. Deep in Saturn's cloud decks, water, ammonia storms build huge charge separations. When a bolt rips through, it blasts radio energy across a broad band. In sound, that breadth becomes a rough crack with fuzzy edges. Trains of evenly spaced cracks reveal a long-lived storm as the planet rotates the storm into and out of radio view. Radio catches it through night and cloud, so your ear can discover storms before any camera sees a flash. The great beacon Saturn kilometric radiation behaves like a drum whose tension changes. These waves are born near the polar regions where field lines converge, and their power depends on how electrical currents close through the ionosphere. Here the rings enter as quiet conductors. Sunlight charges ring grains. Micrometeoroids add fresh, charged dust. The planet's rotating magnetic field tries to drag those charges along. Where the coupling is tight, currents flow cleanly toward the poles, and the beacon brightens. Where the coupling is loose, currents slip, the beacon softens, and the overall rhythm shifts. That is why the beacon's beat drifts with seasons and with changing solar wind pressure. It is a living clock, not a rigid metronome. Ring range sounds gentle because its physics is subtle. From the inner rings, a haze of charged water molecules and nanograins drifts along field lines and falls into the equatorial atmosphere. Water binds electrons in some layers and adds ions in others, reshaping the electrical paths that currents prefer. The magnetosphere responds by changing how and where energy flows. In audio, the bed can lose warmth, the beacon can detune, and the birds can change their pattern. Over months, the effect waxes and wanes with ring geometry and sunlight, so the color of the soundscape follows the seasons. Where does Enceladus fit? The small ocean world feeds a wide torus of water group plasma along its orbit. When Cassini moved through or near that torus, the baseline often thickened and the birdsong shifted because the extra particles changed how waves grow. In plain words, add more players to the band, and the harmony changes. A crucial point about turning data into sound keeps everything honest. The translation rules are fixed. Frequencies measured by the instrument always map to the same audible keys. Measured power always maps to loudness. A rising sweep in your headphones reflects a real rise in measured frequency, not an editor's choice. 1 minute of audio is 1 minute of spacecraft time. Teams then cross-check. Dust pops line up with the dust counter. Bright hiss lines up with strong auroras. Lightning cracks match bursts seen by other radio receivers. And Whistler sweeps match magnetic readings that show electrons streaming along specific field lines. The soundtrack is not a remix. It is a readable record. If you want one picture to carry with you, use the river. Saturn's magnetosphere is a river of charged particles flowing along magnetic banks. The rings are ice cliffs that dip into the flow, adding and removing tiny streams of charge. Where the banks narrow, the river speeds up and sings in higher notes. Where fresh water pours in, the current hisses and the pitch shifts. When pebbles strike your canoe, you hear pops. When distant thunder rolls, you hear cracks. The river never stops. The song never quite repeats, but the rules that shape it stay the same. This why matters, because it turns a spooky ambiance into a readable logbook. Once you hear a clip and can say, "Dust is rising, hiss is brightening, chorus just turned on, beacon drifting," you are not just entertained, you are doing space weather. The same physics shows up at Earth, at Jupiter, and likely around planets circling other stars. Saturn is a classroom where the instruments sing and your ears do the math. Next, we'll step back and trace how Cassini's team built these ears, the wire antennas, the receivers, the calibrations, and the checks that kept the music true. Understanding the craft behind the sound will make every future clip clearer and every eerie note more trustworthy. Let's step behind the sound and look at the ears that made it possible. Cassini's radio and plasma wave science experiment RPWS had one job: feel tiny changes in Saturn's electrical and radio environment and report them faithfully. Long wire antennas unfolded like fishing rods from the spacecraft to sense the local electric field. In a few bands, a compact coil picked up magnetic wiggles. Paired with ultra-quiet receivers, these sensors let Cassini hear the planet's plasma, the way a microphone hears air, translating invisible motion into measurable voltage. Keeping that hearing honest started with hardware discipline. The antennas sat far from noisy electronics and fed low-noise preamps. Engineers characterized their response on Earth, then rechecked it in space using built-in calibration tones and by pointing at known radio sources. If gain drifted with temperature, they corrected it. That is how US stayed trustworthy for more than a decade in a harsh, changing environment. The receivers were stacked like lenses. A low-frequency path tracked slow, rolling variations, the realm of hiss and deep rumble. A mid-frequency path caught whistlers and chorus, the quick birds. A high-frequency path watched Saturn's radio beacon and lightning, where energy splashes across wide bands. Each path sampled narrow slices of time and frequency, and the onboard computer packed those slices for downlink. On Earth, teams stitched them into spectrograms, time on one axis, frequency on the other, so you could literally see the song before you heard it. Now the translation. The rules that turn numbers into sound were fixed. A measured frequency always mapped to the same audible pitch. A measured power always mapped to the same loudness. If a note rose, it rose because real energy moved upward in frequency, not because an editor wanted drama. When natural frequencies sat far above human hearing, engineers applied a constant scale factor to shift them downward without stretching time. 1 minute of audio remained 1 minute of spacecraft time. Dust pops came for free. When a grain of ring ice slammed into Cassini's skin at several kilometers per second, it vaporized into a hot, ionized puff that drove a tiny current surge. The antennas and preamps felt that surge as a sharp spike. The US recorded the spike at the instant of impact. Because the cosmic dust analyzer also counted hits, the team could compare both records. More spikes should mean more grains. Orbit after orbit, they lined up. That cross-check turned an eerie crackle into a reliable dust map. Cross-checks extended across the payload. When auroral hiss swelled in the audio, the ultraviolet spectrometer often saw brighter polar curtains. When a jagged crack tore across the sound, other radio receivers agreed, and cameras later caught storm clouds. When chorus lit up, the magnetometer and plasma instruments recorded electrons flowing along field lines. US was not a soloist. It was a disciplined section in a full orchestra. Agreement between instruments gave confidence that each sound had a physical cause. Spacecraft can sing by accident, so engineers suppressed hums and buzzes of their own making. Power supplies, reaction wheels, and transmitters all carry tones. The team mapped those signatures early, marked their frequencies, and filtered or scheduled around them. They also tracked how the spacecraft's own electrical charge shifted as it moved through plasma and corrected for it when interpreting slow drifts. Result: when you hear a tone glide, you are tracking Saturn's environment, not a wheel spinning or a heater cycling. US carried a Langmuir probe too, a small metal tip that dipped into the plasma to taste its density and temperature. Think of it as a thermometer and dipstick for the soup of electrons. Those readings told the team whether a change in the soundtrack came from a real environmental shift or from spacecraft charging. If the probe said density jumped and the hiss deepened at the same moment, they could claim a clean cause and effect. How do numbers become the clip in your headphones? First, raw voltages are calibrated into physical units. Next, the data are arranged into time frequency tiles. Then the sonification code plays those tiles by assigning each frequency bin to a piano key and each power level to loudness. To keep the result listenable without losing truth, engineers compress the dynamic range slightly. Quiet things come up a bit. Loud things come down a bit using the same curve for every pass. No hand tuning from clip to clip, no hidden knobs. Because bandwidth from Saturn is precious, US alternated modes. Sometimes it scanned a broad range coarsely, like a wide-angle lens. Sometimes it zoomed on a narrow band with high time resolution, like a telephoto catching a hummingbird's wings. The audio you hear is often built from these focused modes, stitched back into continuous time. If a minute goes silent in a certain band, that is a mode change, not a missing note. Timekeeping made the story tight. The spacecraft clock stamped every packet. Ground teams aligned those stamps with Cassini's path and attitude rolling, transmitting, crossing the ring plane. That alignment is why researchers can say, "This crack happened as we grazed a dusty lane," or "The beacon peaked as the pole rotated into view." The narrative in the sound only works because timing was nailed. Finally, there is the human loop. A small group listened, really listened across thousands of orbits. Patterns the eye might miss on a crowded plot jumped out to the ear. A new layer in chorus, a repeating train of electrostatic discharges, a faint thinning of the bed during ring-rain geometry. Ears flagged the moments. Then the math chased them down. That partnership between perception and measurement is how eerie art turned back into hard science. In short, quiet antennas, disciplined receivers, fixed rules, ruthless cross-checks, and patient listening. That is the craft behind Saturn's song. When you press play, you are not hearing a soundtrack laid under pictures. You are hearing a calibrated instrument turn a living environment into something your brain was built to understand sound. Before we go deeper into what the rings are doing to Saturn's space weather, we should clear up the biggest misunderstanding. Space is not a concert hall. There is no air around the rings to carry the ordinary kind of sound that moves from a guitar string to your ear. What you hear in those eerie clips is electricity speaking through instruments, then translated carefully and consistently into audio so a human brain can grasp complex behavior in seconds. That translation is not decoration. It preserves time, it preserves relative power, and it preserves the shape of the original signals. If a tone rises, it is because energy really climbed in frequency. If a bed of noise deepens, the measured power truly grew. You are not listening to special effects, you are listening to physics. This is why the rings sing without vibrating like a bell. Their countless ice grains are part of an electrical environment. Sunlight charges them. Micrometeoroids chip them and loft a haze. Saturn's rotating magnetic field tries to drag those charges along, and the rings either go with the pull or slip against it. That choice, tight coupling or sliding, changes how currents flow along field lines toward the poles. Currents feed auroras. Auroras feed radio beacons. The beacons and background plasma fill Cassini's receivers, and the translation lets you hear the difference between a quiet day and a stormy one, between a clean lane and a dusty gap, between a magnetosphere breathing softly and a magnetosphere being squeezed hard by the solar wind. If the modern clips feel new, the story began decades ago, when Voyager 1 and 2 swept past Saturn in 1980 and 1981. Their plasma wave instruments recorded the first clear tapes of the planet's radio voice, Saturn kilometric radiation, swelling and fading with the poles. Those passes prove that giant planets carry natural radio beacons tied to auroras, and that bursts and whistles can trace electrons racing along magnetic rails. Cassini inherited that legacy, added sharper ears, and then stayed for 13 years to hear Saturn change with seasons, ring geometry, and storms. In its final year, the grand finale dives threaded the narrow gap between the innermost ring and the cloud tops, letting the instruments catch ring rain and dust hits up close. The soundscape gained depth because the spacecraft dared to fly where the voices were loudest. Why does sonification help when plots already exist? Because hearing excels at patterns in time. Your ear separates layers automatically. A spectrogram shows the same information, but it takes training to read quickly. Audio gives you a gut sense right away. A bright, rising bird song means whistlers and chorus are active. A rough crack says lightning. A spray of clicks says dust. A thinning bed hints at ring rain changing conductivity in the upper atmosphere. After a few examples, you can read minutes of data in real time. Then go back to the numbers with sharper questions. Listening does not replace analysis. It focuses it. There is also a human reason the clips resonate. Sound makes a distant, airless world feel close. You can imagine the spacecraft moving through a living place because the soundtrack carries motion, tension, and release. A single rising whistle puts you on a magnetic field line arcing toward the pole. A sudden sizzle of dust puts you inside a gap crowded with tiny projectiles older than Earth. A rolling beacon under everything reminds you that a planet-sized engine is turning, always turning, with its rhythm altered by seasons and storms. The audio is not just a teaching tool. It is a way to feel scale without pictures shouting at you. Still, the translation must stay honest. Engineers lock the mapping from measured frequency to audible pitch and from measured power to loudness, then hold it constant across orbits. They compress dynamics with one fixed curve, so quiet features are audible without letting loud ones clip. But they never hand-tune a particular pass. They label known spacecraft tones and filter them. They cross-check with other instruments. Dust spikes with a dust analyzer, hiss with aurora imagers, lightning with radio receivers and cloud cameras, chorus with magnetometer and plasma readings. If a feature does not line up, it does not get a dramatic name. The discipline protects the wonder. Now that the ground rules are clear, listen again to what the rings are actually doing in this electrical weather. The inner rings leak charged water molecules and nanograins that slide inward along magnetic field lines and fall into the equatorial atmosphere. Water binds electrons in some layers and adds ions in others, reshaping how currents close through the ionosphere. When those paths change, the polar beacons detune and the bed of hiss shifts color. At the same time, sunlight changes ring charging with local time and season, while meteoroid showers can spike dust production for hours to days. The result is a soundtrack that never quite repeats. It is seasonal without being predictable, and local without being random. The rules are steady, the players are restless. There is a useful mental check whenever a clip goes viral under a flashy title. Ask what voice you are hearing. If you hear discrete clicks, you are listening to dust strikes at the spacecraft, not the roar of solid ice. If you hear a broad, breathy wash rising and falling, that is auroral hiss tracking electron precipitation, not wind across stones. If you hear birdsong gliding and stacking, that is chorus and whistlers mapping the flow of high-energy electrons, not a choir in the rings. If you hear a rough, ragged crack, that is lightning from deep storms or a strong packet of electrostatic discharges, not rocks grinding. Make that habit, and the mystery stays magical without drifting into myth. In the next part, we will follow the ring's influence outwards, how Enceladus feeds a wide torus of water-group plasma, how that reservoir alters wave growth, how injections from the outer magnetosphere light up the birds, and how the solar wind's pressure sets the scene. By watching the whole circuit, from tiny grains to planet-scale currents, the song turns into a system you can track. And once you can track it, the eerie becomes understandable without losing its power to make you feel small, curious, and very awake. Zoom out from the rings to the wider circuit that gives them power. A small moon, Enceladus, orbits inside Saturn's magnetic bubble and leaks an ocean into space. Its south polar geysers launch water vapor and flecks of ice high above the surface, where sunlight and charged particles split the vapor into neutrals and ions. Over time, the material spreads into a thick torus that circles the planet along the moon's path. Cassini discovered the plume in 2005 and flew through it many times, sampling chemistry and density with INMS, UVIS, and CAPS, while MAG traced field changes and RPWS listened. Here is the chain that links the plume to the song. Saturn's magnetic field tries to make plasma rotate with the planet. Physicists call that corotation. Fresh neutrals drifting near Enceladus move slowly because they do not feel the magnetic field. The moment they become ions by sunlight, collisions, or charge exchange, they snap into the field's grip and must be accelerated up to the planet's rotation speed. That pickup process taps energy from the rotating flywheel and pours it into waves. It also seeds ion cyclotron tones and helps grow Whistler mode and chorus emissions when energetic electrons are present. In plain words, the torus is a fuel line for sound. Cassini's payload showed the pieces of this engine working together. Plasma spectrometers saw cold newborn ions alongside hotter, older populations. The magnetometer watched the field bow outward into a rotating current sheet, stretched by the weight of added plasma. The dust analyzer counted grains in and near the plume. At the same time, RPWS spectrograms brightened with hiss and chorus whenever the spacecraft crossed denser parts of the torus. Add water to Saturn's space river, and the river grows louder. That river does not simply flow, it churns. Because Saturn spins fast, field lines near the equator that carry extra mass can become unstable. Patches of denser plasma trade places with lighter patches in a slow rolling exchange called interchange instability. When that happens, hot plasma from farther out rushes inward while cooler material moves out. Each inward rush delivers fresh, high-energy electrons that feed chorus. In audio, this shows up as sudden, bright birds gliding over the background wash. Now pull back to the boundary, where Saturn's bubble meets the solar wind. The wind's pressure rises and falls as the sun sends out fast streams, shocks, and gaps. When pressure increases, the magnetosphere compresses, field lines tighten, currents strengthen, and radio beacons grow louder. Cassini often recorded stronger Saturn kilometric radiation during compressions, along with thicker hiss and more energetic whistlers. To a listener, it feels as if the whole key of the soundtrack shifts upward, then relaxes again when the pressure eases. Rotation adds its own rhythm. At Earth, a tilted magnetic axis acts like a lighthouse. At Saturn, the magnetic axis is nearly aligned with the spin, so there is no simple sweep. The radio beacon's period drifts because it is set by how currents close through the ionosphere, not by a rigid geometric beam. That is where the rings and the Enceladus torus matter again. Ring rain changes conductivity near the equator. The torus changes it along the moon's orbit. Seasonal sunlight changes both. The result is a living clock whose beat responds to plumbing, not just to spin. Put these threads together, and a minute of audio becomes a map. A deepened bed with grainy edges and busy birds usually means the torus lies below or that a fresh injection just arrived. A slow rolling swell in the beacon beneath those layers hints that the magnetosphere is under solar wind squeeze. A sudden quieting of birds with a thinner bed points to a lull or to a geometry where ring rain has temporarily altered the current paths. If dust clicks right on top, the spacecraft is near a dusty lane or crossing the ring plane. Remember, sonification is fast and intuitive, but it must be disciplined. Teams anchored sound to calibrated numbers and let multiple instruments vote. If chorus blooms, the spectrometers should show hot electrons. If hiss swells, aurora imagers should brighten. If the beacon surges, the magnetometer should see stronger currents or a compressed field. Only when the votes aligned did the song become a diagnosis. That method kept wonder without letting myth creep in. Back near Enceladus, the interplay grows richer still. The plume is not steady. It waxes and wanes with tidal flexing of the crust and with long-term vent changes. When output rises, the torus brightens and the pickup engine feeds more wave power into the system. On those days, the bed turns weighty and chorus becomes busy across wide bands. When output falls, the opposite happens. The river quiets and the birds thin. The rings join the act by supplying nanograins and water from the inner edge that drift inward and fall into the atmosphere, changing conductivity where currents close. All these effects came into sharp focus during Cassini's grand finale. Diving between the innermost ring and the cloud tops, the spacecraft flew inside the tightest current systems, sampling regions where ring rain bites hardest. The bed thinned and shifted as conductivity changed beneath the path. Dust pops arrived in bursts as tiny grains brushed the hull. The beacon rolled underneath like a tide pulled close to shore. Those passes stripped the soundtrack to essentials and made the roll of the rings as quiet conductors impossible to miss. Think of the whole picture as a network of faucets, flywheels, and rails. The sun sets the pressure from outside. Rotation supplies the flywheel that stores energy. The rings and Enceladus open and close faucets that add mass and change conductivity. Magnetic rails guide charged particles to the poles. Waves grow where free energy is available and fade where it is not. US turned that network into something the ear could follow. Learn the voices, and the map appears without a single frame of video. Let's clear the fog around those eerie clips and make them useful. When people say Saturn's rings are singing, they mean audio built from Cassini's electric and radio measurements. No air near the rings is vibrating. What you hear is a careful translation, fixed rules, no drama knobs of fields and particles into sound, so your brain can follow change over time. Think of each clip as a weather report spoken by the magnetosphere, with the rings acting like a quiet conductor behind the orchestra. Start with 3 listening rules. First, pitch equals real frequency. If a tone climbs, energy truly slid upward in the measured bands. If it falls, it slid downward. Second, loudness tracks measured power. When the bed swells, the waves really grew stronger. Third, time is honest. 1 minute of audio equals 1 minute of spacecraft time. No montage. No edits. With those rules, the clip becomes a moving graph you read with your ears. Now meet the 4 main voices. Pops are dust grains pinging Cassini and kicking tiny voltage spikes into the antenna's pure percussion. Hiss is the breathy bed from auroral electrons streaming into the poles. Whistlers and chorus are the birds. Slender glides and layered calls that reveal how high-energy electrons are being organized along magnetic rails. And underneath everything rolls Saturn kilometric radiation, the planet's radio beacon, waxing and waning as currents close through the ionosphere. The rings steer all of this by trading charge and mass with the planet, and by nudging where those currents flow. Walk through a classic episode, a storm season, deep in the cloud decks. A water-ammonia thunderhead builds charge. Cassini hears it first as jagged cracked trains, broadband bursts called electrostatic discharges, repeating as rotation brings the storm into and out of view. At the same time, chorus gets busy because energetic electrons are being injected and organized. The beacon brightens as currents strengthen, and the hiss thickens over the poles where auroras flare. You don't need a cutaway shot. The sound alone tells you the system is energized. Now the ring-rain geometry. The inner rings shed charged water molecules and nanograins that slide into the equatorial atmosphere. That changes the ionosphere's conductivity, the electrical paving where currents prefer to close. In audio, the effect is subtle but real. The bed cools a little, the beacon detunes, and the birds may soften in certain bands. Stack many passes and the pattern lines up, with ring longitude and season. What the rings shed today can retune what the poles sing tonight. A third episode lives near Enceladus. The moon's geysers feed a wide torus of water group material along its orbit. When neutrals become ions, they must be picked up to Saturn's rotation speed, drawing energy from the planetary flywheel. That pickup process feeds wave growth. In sound you hear a weightier bed, richer hiss, and birds arriving in busy layers. Add an interchange event, a blob of hot plasma rolling inward, and the birds brighten suddenly, then fade as the energy diffuses. A tiny ocean world ends up changing the music of a giant. Because these clips travel far online, myths grow fast. Myth 1. The rings vibrate like a crystal bowl. They don't. Ring particles are too loosely bound to ring like a bell. They steer currents instead. Myth 2. The audio is fake. It isn't, as long as frequency, pitch, and power, loudness mappings stay fixed and documented. Myth 3. The sounds prove there's wind near the rings. There's essentially vacuum. The voice rides on electromagnetic waves, not air. Why does this matter beyond chills? Because listening speeds up science. A trained ear can skim hours of data and flag the minutes worth deep analysis. A new chorus layer, a repeating cracked train from a nightside storm, a quiet detuning that marks ring rain. Sound points the math to the right seconds. It also invites everyone in. Without reading a dense plot, you can feel the magnetosphere breathe, starting, peaking, fading, switching key. The system stops being a diagram and becomes a place. There's a bigger horizon, too. The same physics shapes Earth's auroras and Jupiter's roaring radio storms. When we dream about detecting exoplanet magnetospheres, we are really dreaming about hearing distant versions of these voices. A beacon rolling under hiss and birds. Saturn with rings that rain and an ocean moon feeding a torus is a perfect training ground. Learn to read its soundtrack and you're ready to read others. Keep a simple checklist in mind. If pops surge, Cassini is in dust, think ring plane crossing or a dense lane. If hiss swells and the beacon rises, currents are strong, and auroras are active often during solar wind compression. If birds stack in bright layers, energetic electrons were just injected, sometimes by interchange motion deeper inside. If the bed quietly cools and the beacon detunes, ring rain likely shifted the ionospheric pathways. Hear those 4 patterns, and you can narrate a minute of Saturn without seeing a single frame. You don't need fancy visuals for any of this. A slow pan across the rings, a wide, calm view of the planet, a distant shot of Enceladus venting into black. Let the audio carry the action. Let the hiss swell as the pole brightens. Let the birds burst when energy arrives. Let the pop spike as the ring plane rushes past. Your eyes rest. Your ears do the flying. Hold one picture as we continue. A giant electrical river around a spinning world. The rings dip icy fingers into that river, adding and removing charge. Enceladus pours water into it. The sun pushes from outside. Waves rise where free energy appears and fade where it's spent. Cassini's antennas turned that river into sound. Next, we'll pair famous Cassini clips with plain language, what you're hearing. Breakdowns so each eerie note becomes a cause you can name. Let's put sound to scenes you can picture while the music does the explaining. Think of 5 emblematic moments from the mission and what each one tells you in plain language. First, the polar beacon breathing under an aurora. The track opens with a low, rolling presence that swells and eases like ocean tide. This is Saturn's natural radio lighthouse rising, where magnetic field lines converge near the poles. Then the bed fattens, the hiss brightens, and a slow, pulsing beat stands out. That means the magnetosphere has tightened. Solar wind pressure has pushed the boundary inward. Currents have strengthened, and more electrons are diving into the upper atmosphere along the rails. In sound, the whole key shifts upward, then relaxes as the squeeze passes. Second, the night-side storm that speaks before any camera can. The hiss is cruising when a ragged crack tears across the band, followed by another, then another, evenly spaced as if something is turning. These are bursts from deep-water ammonia thunderheads radio packets called electrostatic discharges that punch through cloud and darkness. Each train repeats as rotation brings the storm into view, then hides it again. Chorus often brightens around these moments because energetic electrons are stirred and organized by the disturbance. Third, a ring plane crossing where dust writes percussion. The airy bed continues, thin birds glide, and then the first pinpricks arrive. Click, click, click. They thicken into a sizzle. Each pop is a microscopic ice grain striking the hull and flashing into a tiny cloud of plasma that the antennas feel as a voltage spike. The sizzle swells, peaks, and then eases. You have just heard a gap from entry to exit with no need for a diagram. Sometimes 2 distinct humps appear. That means 2 denser sheets separated by a cleaner lane. No visuals required. The rhythm tells the geometry. Fourth, a pass through the Enceladus neighborhood where a moon tunes the key. The baseline grows heavy. Birds multiply and layer. This is the plume's wide torus, adding mass to the magnetosphere. New ions must be accelerated up to Saturn's rotation. That pickup siphons energy from the planetary flywheel and feeds waves. The chorus brightens, hiss thickens, and the beacon often lifts a little, as if the whole orchestra gained a section. If a blob of hot plasma rolls inward an interchange event, the birds flare suddenly, then fade as energy spreads. Fifth, a grand finale dive. The most intimate passages of the mission. The track begins spare and close because the spacecraft is sliding between the inner ring edge and the cloud tops where ring rain bites. The bed is thinner, slightly cool in color. The beacon below rolls slow but near, like surf under a cliff. Dust arrives in tight bursts quick, bright sprays that say small grains are brushing the shields. A single rough crack may ride over the top when lightning pops far below. The scene is tense yet controlled, the sound of a spacecraft threading a live machine. Now focus on the classic birds that slide up in pitch, the whistlers that give these recordings their name. Hear a delicate tone begin low and climb smoothly, sometimes in steps like a scale. That glide tells you electrons are moving along a field line into stronger magnetic regions where their natural frequencies rise. When several neighboring field lines light up, you hear a choir of staggered glides, a textbook chorus. If a glide falls instead, higher notes have arrived first because the wave dispersed as it traveled. Either way, the direction encodes location and motion. There is a subtler character that matters. The gentle detuning when ring rain shifts the electrical pathways. You will not hear a single dramatic cue. You will notice that the wash loses a little warmth, that the beacon's pitch slides off its earlier center, that birds settle onto slightly different shelves. Stack several passes with the same geometry, and it becomes obvious. Charged water molecules and nanograins have fallen from the inner rings, bound electrons in some heights, added ions in others, and redirected how currents close through the ionosphere. The magnetosphere changes key without changing tempo. Use a simple 3-step habit whenever a new clip plays. First, name the layers: pops, hiss, birds, beacon. Second, track their change. growing, thinning, gliding, detuning. Third, tie each change to a cause. Dust lane, auroral surge, fresh electron injection, ring, rain geometry, solar, wind, squeeze. The spacecraft flew here. The system did this. The energy came from there, and the rings or Enceladus nudged it that way. If you want one more mental picture, keep the orchestra in mind. The beacon is low brass that sets the room shaking. Hiss is strings holding the bed. The birds are woodwinds painting motion on top. Dust is the snare that snaps you to attention. The conductor stands off stage, made of ice and sunlight and electricity. The rings, quiet hands on a giant dimmer. When the conductor turns, the brass rises, the strings darken, the woodwinds scatter, and the snare rolls. The players are natural fields and particles, and the score is written by rotation, sunlight, seasons, and meteoroids. All of this rests on fixed rules. Frequency maps to pitch, power maps to loudness, 1 minute maps to 1 minute. No hand-tuned crescendos, no cinematic fades. That restraint is why the clips carry both wonder and trust. They are eerie and honest. They let a planet speak across a vacuum in a language your senses can master, even with simple visuals drifting by. A calm wide shot of the rings, a polar glow hinting at aurora, a distant plume against black. Next, we open the rings themselves and read them as an electrical device. Why sunlight, season, and meteoroid rain decide how strongly grains couple to the field, how spokes can arise from charging, and how inner edge material can pour down magnetic rails to retune the ionosphere in hours. With that in mind, every future clip becomes a diagnosis, not just a mood. Treat Saturn's rings like an electrical device. Each ice grain is a tiny electrode in plasma. Sunlight ejects electrons, photoemission. Magnetospheric electrons stick back on, and micrometeoroid hits spit out vapor and nanodust that charge almost instantly. The balance of these currents sets each grain's electric potential. Change the light, the plasma, or the dust supply, and you change the voltage on billions of grains at once. Seasons, storms, and geometry quietly retune the ring system. Day versus night sets the first dial. In sunlight, grains tend to go slightly positive. On the night side, photoemission shuts off and grains soak up electrons, drifting negative. Fine dust responds fastest. That matters because the force on a particle scales with charge times electric field. Double the charge and the same field does twice the work on a tiny grain. The field comes from motion. Saturn's magnetic field rotates with the planet and tries to drag plasma with it. Corrotation. Where plasma lags, a radial electric field appears. That field, plus smaller fields from waves and charging clouds, acts on charged dust. Big blocks ignore it. Micron and submicron grains feel it. In special conditions, the combo can levitate the finest grains for minutes to hours just above the ring plane. Enter the spoke's radial features that stunned Voyager and returned in the Cassini era, especially near equinox. A spoke is a patch where electrostatically lifted dust hovers above the B ring, nearly corrotating like a faint stencil. They can form in minutes and fade in hours. Near equinox, with the sun almost edge-on, photoemission is reduced, so grains stay negatively charged longer on the night side. A meteoroid strike or a local plasma burst then lifts the lightest dust and stamps a spoke that rides with rotation. Lighting explains the look. In backscatter, the lifted veil blocks and diffuses sunlight, so spokes appear dark. In forward scatter, they can brighten. Either way, they are electrical weather, charging, local fields, and corrotation working together. Because the dust is tiny and elevated, it settles slowly, so the pattern drifts like a minute hand. What does a spoke do to the sound? No clang, it is not a bar, but a spoke alters plasma near the plane by adding fine, highly charged dust, and by perturbing electron densities. That can tweak the very low-frequency bed and, when widespread, alter how currents close through the ionosphere. Across many Cassini passes, subtle shifts in His and in the beacon show up during spoke-friendly seasons. The effect is modest, clip by clip. Over months it nudges the tone. Meteoroid rain is another switch. When a stream of micrometeoroids sweeps Saturn, impacts dump fresh nanograins and vapor, thickening the charged haze above certain radii. That raises effective conductivity along nearby field lines and seeds waves. In audio, you would not hear a new instrument. You would hear a mix change, hiss a touch grainier, pops more frequent near the plane, birds a bit busier where new electrons are picked up. Now focus on the inner edge ground zero for ring rain. Tiny water group clusters and nanograins peel off the D and inner C rings and ride magnetic field lines into the equatorial atmosphere. Water captures free electrons in some layers and feeds ions in others, rewiring where currents prefer to close. During Cassini's grand finale dives, field lines tied to these inner edges produced a thinner, cooler audio bed and slight detunes in the beacon. Consistent with a changed ionosphere, think of the rings as three adjustable knobs. Charge state is set by sunlight and plasma. Mass loading is set by dust and vapor sources, meteoroids and Enceladus. Geometry is set by season and viewing. Turn the charge knob, spokes get easier or harder to launch. Turn the mass knob, haze, and pick up change, making His thicker or thinner, and birds livelier or quiet. Turn the geometry knob. How efficiently field lines connect to the ionosphere shifts, detuning the beacon. Their interplay is why the same region can sound different on 2 days that look alike. Scale keeps expectations sane. The electrical forces that lift micron grains are huge for those grains, but tiny for house-sized blocks. Big chunks are ruled by gravity and collisions. The circuit lives in the fines, frost and powder. A camera barely resolves, but RPWS can feel through the plasma they perturb. When a headline shouts that the rings are singing, this is the choir. Countless submicron voices cued by sunlight and spin. Operations use these cues. If ARP's pops rose and the dust analyzer agreed during a ring plane crossing, pointing constraints tightened. If His thinned and the beacon detuned near predicted ring rain longitudes, that was expected circuit behavior. If images flagged spokes, analysts looked for matching low-frequency changes and for chorus behavior as the spoke rotated under high-latitude field lines. There is one more lever, the solar wind. A compression can raise the whole mix beacon stronger, His brighter, birds busier, while spokes or ring rain fine tune the color. The system is layered. Outside pressure sets the volume. Rings and moons shape the equalizer. 1 minute of audio can feel familiar yet distinct. The rules stay, the settings shift. Put it together and the rings stop being scenery. They are the control surface of a magnetized machine. Sunlight, season, and meteoroids set the surface charge. Corrotation supplies the field. Enceladus supplies mass. Gravity keeps the disk razor thin. Cassini, with quiet antennas and fixed rules, turn the result into an honest soundtrack. Once you hear it that way, a faint hiss is a status light. A glide is a current-changing rails, and a spray of pops is the ring plane stepping into the circuit. Next we will climb the rails to the poles, where those currents light auroras and drive the radio beacon that underpins every clip so you can match what your ear hears to what a camera would see above the rings. Climb the magnetic rails to the poles and watch how the circuit closes. Field-aligned currents, electrical rivers, flow along Saturn's invisible lines from space into the upper atmosphere. Where those rails meet thin air, electrons plunge downward and excite atoms and molecules. To a camera, that becomes aurora, ovals of light encircling each pole. To a radio ear, the same region is a power plant. The plunging electrons trigger a natural amplifier that turns their motion into radio waves. That amplifier works because electrons spiral around magnetic field lines like runners on a helical track. Under the right conditions, their motion transfers energy into specific radio frequencies, and the emission grows rapidly like a whistle that the magnetosphere blows when fast electrons stream into the polar sky. Cassini's receivers cannot play those frequencies directly. They sit far above human hearing, so engineers shift them down by a fixed factor. The shape, timing, and relative loudness are preserved. Only the pitch is moved so your ear can follow the story. The tide you hear beneath many clips is Saturn kilometric radiation, the planet's radio beacon. It is kilometric because its wavelengths are kilometers long. Frequencies mostly in the tens to hundreds of kilohertz. SKR is strongly beamed. It does not spray everywhere. It fans out in hollow cones that sweep past the spacecraft when geometry lines up. Cassini hears it loudest when the cone crosses the line between the source and the spacecraft. Auroras organize the soundtrack because they organize current. When the polar lights brighten, more electrons are pouring down the rails. The ionosphere, Saturn's electrically active upper atmosphere, closes those currents like a glowing switchboard. If ring rain has removed free electrons at certain heights, that switchboard changes its resistance. Currents take new routes, and the beacon shifts key. Add a solar wind squeeze from outside, and the rails carry even more load. Hiss thickens, birds get busier, and the beacon rises. What would you see while you hear it? Picture a UV camera pointed at the North Pole. A bright oval arc surround the cap, fluttering with small curls and beads. Each curl is a packet of energy sliding down a rail. When those curls multiply, US hears the hiss swell. Minutes later, layered birds chorus, paint the spectrogram because fresh electrons have been injected and organized by changing fields. If a deep storm is active on the night side, broad, ragged cracks ride over the bed. Radio bursts from lightning that a visible camera may miss. Another polar clue is polarization, the twist of a radio wave's electric field. SKR is often strongly polarized, which helps teams separate true planetary radio from any stray spacecraft hum. In practice, the receivers split left-hand and right-hand modes and identify which cone they are crossing. It pins down where the emission was born and which hemisphere sings loudest that hour. Because SKR ties to magnetic strength, the pitch you would assign before translation depends on altitude. Closer to the planet, where the field is stronger, the preferred frequency is higher. Farther out, it is lower. As the emission region migrates up and down the rails with changing conditions, the spectrum slides accordingly. Translated for headphones, that shows up as the beacon changing color while keeping its pulse an honest shift in where power is being generated, not a mixing trick. Now tie the poles back to the rings. Inner edge ring rain rewires the equatorial ionosphere, and those changes ripple to the polar switchboard along connected field lines. The result can be a beacon that wanders in period over weeks and seasons. One reason Cassini showed Saturn's radio period is not a rigid rotation clock. The rings are not twisting the planet faster or slower. They are changing the circuit that sets the drum's tension. Enceladus adds its own touch. Mass loading along the moon's orbit changes how currents flow, which can brighten hiss and birds when the pickup engine is active. There is choreography and local time, too. On the day side, the solar wind presses directly on the magnetospheric bubble. On the night side, stretched field lines can snap back and fling particles inward in injections that sound like sudden, bright birds. At certain longitudes, the inner rings couple more strongly, so the ionosphere accepts more current with less resistance. Those sectors become auroral hotspots in radio. You do not need a map to feel it. A run of clips from successive orbits will teach your ear the rhythm. If the physics sounds forbidding, the pictures are simple. Rails guide energy. The rings in Enceladus set how much charge and mass the rails must carry. The sun squeezes from outside. Where rails meet air, light, and radio blossom. US took the blossom's radio and made it audible without tricks. That is why a rising tide beneath your track is not just a mood. It is a measured increase in power from a real auroral engine. There is a practical payoff. By watching SKR and HISS while imaging auroras, teams could forecast space weather at Saturn. A surging beacon plus thickening HISS usually meant stronger polar curtains coming into view. Busy birds hinted that injections were underway. During the grand finale, that awareness helped controllers choose safe attitudes for ring plane dives. Carry one polar scene into the rest of the story. The camera shows a thin auroral arc flickering like a heartbeat. In your headphones, the beacon rolls, steady but alive. A faint wash grows. Birds glint along the top. For a minute, the arc blossoms, then thins. You know a giant circuit just handled a surge and settled back, because the poles sang and the rings helped set the tune. Next, we will put all the pieces on one page, a clear, memorable blueprint of the machine from rings and moon to rails and pole, so that any Cassini clip you ever hear can be decoded in seconds without pausing the video or showing a single graph. Here is the whole machine on one page, a blueprint you can keep in your head while the audio plays. Picture 6 parts working together. First, the flywheel. Saturn's rapid rotation and global magnetic field store energy and set everything in motion. Second, the sources. The rings and the ocean moon. Enceladus. The rings exchange charge with sunlight and meteoroids. Enceladus feeds water that spreads into a torus. Third, the rails. Magnetic field lines that guide charged particles through the system. Fourth, the switchboard. The ionosphere. A thin, electrically active layer at the top of Saturn's atmosphere where currents close. Fifth, the amplifiers, auroras, and the planet's radio beacon Saturn kilometric radiation that bloom when fast electrons pour down the rails. Sixth, the ears, Cassini's antennas and receivers, which turned fields and particles into numbers that engineers translated faithfully into sound. Energy flows like this. Rotation tries to drag plasma around with the planet corrotation. Where plasma lags, electric fields appear and do work on charges and dust. The rings add and remove charge in tiny mass. Enceladus adds water that becomes ions. Those changes alter how smoothly corrotation holds and where currents prefer to flow. Currents race along rails to the poles, lighting auroras and powering the radio beacon. Outside pressure from the solar wind squeezes or relaxes the whole bubble, changing the game. Cassini samples the result, and, after a fixed pitch and loudness mapping, your ear hears a living circuit. Now turn that blueprint into a pocket decoder. Pops or percussion from dust grains hitting the spacecraft, think ring plane crossings or dusty lanes. Hiss is the breath under everything, electrons streaming into the polar sky. Birds, whistlers, and chorus are slender glides and layered sweeps from high-energy electrons being organized along the rails. The low, rolling presence is the beacon, rising and falling as currents strengthen and geometry lines it up with the spacecraft. The rings and Enceladus steer the whole mix by changing charge, mass, and conductivity. The sun sets the master volume with pressure from outside. Use 3 quick questions while you listen. What layers are present? How are they changing? What in the blueprint could cause that change right now? If pops surge, you are in dust. Check for a ring, plane brush, or a gap crossing. If hiss swells and the beacon rises, currents are strong, often a solar wind squeeze or a sector where ring rain makes the switchboard more conductive. If birds stack bright, a fresh injection of energetic electrons just happened, maybe an interchange event rolling inward from the torus near Enceladus. If the whole bed cools and the beacon detunes gently, ring rain likely redirected current paths along connected field lines. Spokes fit cleanly in this scheme. They are not vibrating bars. They are brief electrical weather levitated fine dust above the B ring when charging and fields line up, especially near equinox. A spoke adds tiny, highly charged grains to the near-ring plasma, nudging low-frequency behavior and, when widespread, the preferred routes for current. In sound, you hear modest, seasonal shifts. The bed's color changes a shade. The beacon wanders slightly. Lightning fits too. Deep water, Ammonia storms build charge. When a bolt fires, it sprays broadband radio that becomes jagged cracks in audio. Trains repeat as the storm rotates in and out of view. Around those times, the birds often grow busy because injections accompany the disturbance. The blueprint says, inner weather can seed outer waves, and the ear catches both. Why the fixed translation matters should now be obvious. Pitch must track measured frequency. Loudness must track measured power. Time must stay true. Hold that discipline, and a rising whistle truly marks energy sliding to higher bands. A swelling bed truly means more wave power. A rolling beacon truly marks geometry and current closure, not editing. That's why agencies publish both spectrograms and audio. Your ear reads the same truth your eye sees on the plot, fast. If you ever want to check eclipse provenance, NASA and ESA releases typically link the instrument, band, and mapping. Make a mental overlay for visuals. A calm, slow pan across the rings pairs well with thin hiss and a few birds' quiet day. A distant Enceladus plume with a weightier bed suggests the Taurus is under you. A polar glow with a rising tide underneath says auroras are active and currents are strong. No fast cutting is needed. The soundtrack carries motion and cause, second by second. Two common confusions fall away with the blueprint. Are we hearing the rings vibrate? No. We are hearing electromagnetic waves shaped by how the rings and moons change charge, mass, and conductivity in a rotating magnetic system. Is the audio fake? No, as long as pitch and loudness mappings are fixed and documented. Sonification is translation, not theater. You can also forecast with your ears. A steady rise in the beacon plus thickening hiss often precedes brighter auroras in ultraviolet images. Busy birds without much dust say injections are active far from the ring plane. A quiet detuning that repeats at certain longitudes hints at ring range sectors you could map with time. During Cassini's grand finale, that ear-first awareness helped the team choose attitudes and anticipate dust sprays without waiting for plots. Hold one last picture. A river wrapped around a spinning world. The rings dip icy fingers into it. Enceladus pours water into it. The sun squeezes it from outside. Rails guide the current to the poles where light and radio bloom. The river never stops, and the song never quite repeats, but the rules keep you oriented. With this blueprint, any Cassini clip becomes a scene you can narrate honestly in real time. What's playing, why it's loud or soft, and which part of the machine moved. In the next section, we'll walk a few famous public clips moment by moment with this decoder in hand, so you can hear exactly which part of Saturn's machine is speaking each time the soundtrack gives you chills. Let's walk through 4 Cassini soundscapes, moment by moment, so your ear learns to read Saturn while simple space visuals drift by. First, the polar beacon breathing beneath an aurora. From the opening second, a low, rolling presence swells under a thin wash. That tide is Saturn's radio lighthouse, lining up while background plasma hums. The hiss fattens, and small glides sparkle on top. Electrons are pouring down magnetic rails and organizing into whistlers and faint chorus, like a sky brightening before dawn. Around half a minute, the beacon peaks and trembles as the magnetosphere tightens, likely under a squeeze from the solar wind. Then the wash eases in slow waves. Currents relax, the birds thin without vanishing, and the beacon settles back. Without a single cutaway, you have felt a polar sector breathe in and out. Next, a night-side storm that speaks before any camera can. A quiet bed holds for a few seconds. Then a ragged, broadband crack slashes across the band. It is too wide for dust and too rough for chorus. It is lightning deep in a water ammonia cloud deck. Another crack follows, then another, spaced almost evenly as rotation carries the storm into and out of radio view. Between bursts, the bed stays steady, a calm stage between flashes. After a strong packet, the birds brighten briefly because energetic electrons have been stirred and organized by the disturbance. By the end of the minute, the spacing repeats, and your ear can time the storm's period from the rhythm of the trains. Now a ring plane crossing where dust writes percussion. The track opens with thin hiss and a few high glides, a calm corridor. Then single pinpricks arrive, click, click slow at first, then gathering into a spray. Each pop is a microscopic ice grain striking Cassini and flashing into a charged puff that kicks the antennas. The spray becomes a sizzle, peaks, and eases. The rhythm alone sketches a gap from entry to center to exit, sometimes a second. Smaller hump follows after a short lull, revealing two denser sheets with a cleaner lane between. You have just heard structure without ever seeing a map. Finally, a grand finale dive, the closest brush with the machine. The bed arrives cooler and slightly thinned, because field lines here connect to the innermost rings and ring rain has altered the ionosphere's conductivity. Beneath the scene, the beacon rolls strong, then detunes a shade as current paths shift under the spacecraft. Tight bursts of pops come in packets, nanograins brushing shields during brief sprays, while a single coarse crack can ride over everything when a distant electrostatic discharge escapes the clouds. By the end, the clicks taper, the bed stays cool, and the beacon rolls on like surf beneath a cliff. You can feel the spacecraft sliding between a ring's inner edge and a planet's roof of cloud. If timestamps help, imagine the auroral clip as a 60-second tide that rises by the 8th second, crests near 30, and ebbs by a minute. Hear the lightning scene as a heartbeat, a crack roughly every dozen seconds turning with the planet. Hear the ring plane crossing as a two-hump hill sizzle up, peak, down, brief valley, smaller rise, then clear. Hear the grand finale as a cool corridor, steady beacon, subtle detune, tight packets of clicks, and a clean glide back to the bed. Once you frame a clip with a simple shape like that, the pattern becomes obvious, and your intuition starts predicting what comes next. Fold in the quiet conductor that shapes every scene. When ring rain strengthens, the beacon's color slides and the hiss loses warmth because conductivity has been rewritten where currents close in the upper atmosphere. When meteoroid streams feed fresh nanograins into the near-ring plasma, pops grow frequent and the wash gains a faint graininess. When the solar wind sends a shock that squeezes the magnetosphere, everything lifts together, beacon louder, hiss brighter, birds busier. Then comes a slow exhale as pressure eases and the key relaxes. This same decoder corrects the easy misreads without draining the magic. If the sizzle sounds like stones grinding, remember there is no air between ring particles and that the clicks come from impacts on the spacecraft, not friction in vacuum. If the hiss suggests wind, remember electrons streaming into the polar sky, faithfully translated to sound by fixed rules. If the beacon's pulse feels like a rotation clock, remember that its beat wanders with season and pressure because currents set the drum's tension, not a tilted magnetic lighthouse. What keeps these scenes compelling is their natural shape. Each has a beginning that invites you in, a middle where energy organizes into patterns your ear can track, and an end that releases tension without effects. Slow, universal visuals let the soundtrack carry motion and cause a calm polar glow as the beacon swells, a dark limb while cracked trains return, a wide pan over the ring plane as the sizzle maps a gap, an inner rim above cloud tops as the cool bed holds steady. The sound is not decoration, it is the story told in a language your ears were built to understand. With a handful of soundscapes like these, you can cover almost any minute around Saturn honestly. Swap in a different pass and the same rules apply. Pop sketch structure, hiss marks, polar rain. Birds reveal injections and order. The beacon carries geometry and current closure. The rings and the solar wind steer the mix, and the whole machine breathes on a timescale you can feel. Once the pattern lands, the eerie becomes readable, and the readable becomes unforgettable. Think forward from Saturn, and you'll hear a family resemblance across the solar system. Earth has its own chorus and hiss. When geomagnetic storms arrive, Our magnetosphere fills with rising birds, just like Saturn's, and the polar sky brightens as currents surge. Jupiter turns the dial to loud. Its radio storms can outshine the sun at certain frequencies. And one small moon, Io, acts like an alternator in the circuit, feeding sulfur and oxygen that load the field and modulate the planet's decametric radio bursts. Uranus and Neptune add quirks, tilted, offset magnetic fields that make their auroral engines wobble in strange rhythms. Different worlds, same language fields, particles, currents, spoken with local accents. That comparison matters because it points beyond the solar system. If a nearby exoplanet carries a strong magnetic field and lively auroras, it may radiate low-frequency radio waves. Shifted into our hearing range with honest rules, that would sound like a slow tide under faint birds, an exobeacon. Catching such a signal wouldn't just be cool audio, it would prove a magnetic shield exists, hint at a restless interior, and sketch the planet's space weather, the protective bubble that helps an atmosphere survive. The physics is universal. Rotation stores energy, a magnetosphere channels it, plasma sources feed it, and the star's wind squeezes it. Saturn is your practice room for hearing that story anywhere. You can try the method right now with simple listening habits. Start any clip by naming layers out loud: pops, hiss, birds, beacon. Track how each changes with time. Do pops bunch, then thin? That's a dust lane from entry to exit. Does the hiss deepen, then ease? Polar electrons are flowing harder, then relaxing. Do birds stack into bright shelves? Fresh energetic electrons were just injected and organized along magnetic rails. Does the beacon wander in strength or color? Current paths are shifting ring rain, solar wind pressure, or geometry may be changing the circuit. Finally, ask whether the pattern holds for more than a heartbeat. Real physics loves coherence, causes leaf signatures that persist long enough to be noticed. If you ever move from listening to doing, the recipe is straightforward in spirit. Begin with calibrated spectra power as a function of frequency and time. Choose a fixed mapping from measured frequency to audible pitch and from measured power to loudness. Keep that mapping constant across passes and say so in the caption. Compress the dynamic range a little, quiet features up, loud ones down using one gentle curve so details survive without clipping peaks. Render 1 minute of data as 1 minute of audio. Publish the mapping with the clip. That discipline keeps the wonder anchored to truth. There are pitfalls worth dodging. Don't let one narrow band dominate. It turns a living scene into a pure whine that hides birds and hiss. Don't stretch or shrink time. You'll break cause and effect. Don't denoise away the pops. They are measurements of dust, not dirt on the tape. If you remove a known artifact reaction wheel hum or a transmitter sideband, say so clearly. Above all, resist adding reverb or music under the science track. The raw instrument is already astonishing because it is nature speaking without a filter. This way of hearing pairs beautifully with simple, reusable visuals. A wide, slow pan across the rings invites the ear to carry structure. The sizzle that swells and eases sketches a gap crossing by itself. A steady polar view with a faint auroral oval lets the ear feel the beacon's tide in the hiss's growth without fast cuts. When the soundtrack is honest, the simplest shots are the strongest. They give attention a quiet place to rest, while the physics unfolds in real time. Because this story travels fast online, keep a myth to truth card handy. The rings vibrate like a crystal bowl. No, the rings steer currents in a magnetized plasma. The sound you hear is radio translated into audio, not air vibrating. Space is silent, so the clip is fake. Space is silent to pressure waves, but not to electromagnetic waves, which antennas can measure and we can map to sound with fixed rules. Those clicks are rocks scraping together. They're dust grains hitting a spacecraft and creating tiny electrical spikes. The beat is Saturn's rotation clock. The beat drifts because currents and geometry set the tension on the drum. The planet's magnetic axis is nearly aligned with its spin, so there's no rigid lighthouse timer. Hold one more perspective that keeps wonder anchored. The rings you see are ancient ice, but their voice is always young, renewed, minute by sunlight, meteoroids, and the pull of a spinning magnetic field. Enceladus is small, yet its ocean feeds a torus that can change an entire planet's weather in space. The sun is far, yet a gust in its wind can squeeze a magnetosphere 1 billion kilometers away and lift a beacon you can hear tonight. Scale is humbling, rules are friendly. Once you've listened with a trained ear, you can stand in front of an eclipse, Saturn, Earth, Jupiter, and narrate what the system is doing without a single graph. So when the next audio crosses your feed, hiss, birds, pops, beacon, give yourself 10 seconds before reading the caption. Name the layers, sketch the cause, see whether your guess matches the description. You'll feel the same jolt of strangeness, but now it lands as understanding. The eerie becomes legible, the legible becomes memorable, and the memory becomes a portable instrument you can use anywhere these fields and particles play. To close this arc, we'll knit everything into a concise cinematic retelling, the whole song from first chill to final clarity, so your video can open strong, breathe in the middle, and end with an echo your audience will carry long after the last frame fades. The voices are ready. The rules are steady. All that remains is to press play and let a giant world speak through electricity and ice. Press play and begin with a breath that isn't air. A faint hiss rises, a slim whistle climbs, and a scatter of clicks pricks the dark. At first, it feels eerie, like a planet whispering. Then the shapes settle into sense. The hiss is auroral electrons pouring down magnetic rails into the poles. The whistle is a whistler, a glide traced by high-energy electrons sliding into stronger fields. The clicks are dust grains, flecks of ancient ring ice, striking a spacecraft and flashing into tiny puffs of plasma. Under it all rolls a slow tide, the planet's own radio beacon, born where the rails meet thin air and currents close. You are not hearing air vibrate. You are hearing fields and particles measured by a machine and translated honestly into sound your brain can read. Stay with the scene and the conductor steps out of shadow. The rings do not ring like metal. They steer. Sunlight charges their grains. Micrometeoroids feed a haze. Saturn's rotating magnetic field tries to drag those charges along. Where the coupling is tight, currents flow cleanly to the poles and the beacon brightens. Where it slips, hiss thins, and birds change their tune. The inner edge sheds charged water and nanograins that fall into the equatorial atmosphere, ring rain retuning the ionosphere, which retunes the beacon. A small ocean moon, Enceladus, pours water into a wide torus. When neutrals become ions, they must be picked up to the planet's speed, tapping the flywheel and feeding waves. Outside, the solar wind squeezes and releases the whole bubble, lifting the key, then letting it fall. The soundtrack is a live circuit, with the rings on the dimmer and the sun on the master volume. The rules that make this music readable are simple and strict. Pitch follows measured frequency, loudness follows measured power. 1 minute of audio equals 1 minute of spacecraft time. Keep those rules fixed, and a rising tone means real energy slid upward. A swelling bed means waves grew stronger, and a drifting beat means current paths changed. Engineers fixed the mapping, cross-checked with other instruments, labeled and filtered known spacecraft hums, and let the rest stand. No reverb, no cinematic swells, just a calibrated ear on a living world. Now let a minute unfold. Pops, bunch, and sizzle. A dusty lane near the ring plane. Hiss, fattens. Polar electrons are flowing harder, auroras brightening where a UV camera would glow. Birds stack in bright shelves. Fresh energetic electrons were injected and organized, often by interchange motion inside the torus near Enceladus. A ragged crack tears across the bed. Lightning from a deep water, ammonia storm. Its broadband burst, repeating as rotation carries the storm into and out of view. The bed cools a shade, and the beacon detunes. Ring rain redirected current paths along connected field lines. The clicks thin, the birds quiet, the tide keeps rolling. Without a single cutaway, you have heard a machine take a breath and let it out. If a spoke forms levitated fine dust above the B ring during favorable charging, the camera shows a faint radial stencil, drifting with rotation. In sound, there is no clang. Spokes are electrical weather, not bars. But when they are common, the low bed shifts color and the beacon wanders a little more, because fine, highly charged grains nudge electron densities and the route's currents prefer. Stack many passes and the pattern emerges with season and geometry. The myth fades, the wonder stays. What makes these clips powerful is not volume, but shape. Every honest track has a clear beginning, middle, and release. The opening invites thin bed, a first bird, a few clicks. The middle organizes busy chorus, thicker hiss, beacon rising, dust peaking. The end lets go. Birds thin, bed eases, tide settles. You can score the entire video with simple, slow visuals, calm pans of the rings, a polar glow, a distant plume because the audio already carries motion and cause. Your viewer doesn't need fast edits, they need room to hear. The story reaches beyond Saturn. Earth's magnetosphere sings the same language. Jupiter roars in it. Exoplanets may too. If one day we catch a distant low-frequency beacon and render it with the same fixed rules, it will sound like a slow tide under faint birds, proof of a magnetic shield, a restless interior, and weather in space. Saturn is where you learn to listen so you can recognize that voice anywhere. So give your audience a decoder they can use in 10 seconds. Name the layers: pops, hiss, birds, beacon. Track their change: bunching, fattening, stacking, drifting. Tie each change to a cause: dust lane, auroral surge, electron injection, ring, rain geometry, solar, wind, squeeze. With that habit, the eerie turns legible, the legible turns memorable, and the memory becomes a tool. They will start predicting what comes next before it arrives. That's when the system stops being a mood and becomes a map. Hold the final picture as the credits approach. A river of charged particles circles a fast-spinning world. The rings dip icy fingers into it and quietly turn the knob. A small moon pours water into it and gives it weight. The sun squeezes it from afar. Rails guide the current to the poles where light and radio bloom. A spacecraft extends thin antennas and listens. The numbers become sound. The sound becomes meaning. The meaning becomes a feeling you can carry. That even in vacuum, a world can speak. And if you listen with honest rules, you will understand what it is saying. When the last note fades, leave a breath of silence, then let the tide return, just for a heartbeat. A reminder that the machine never stops and the song never quite repeats. Somewhere, the hiss is rising, the birds are gathering, the beacon is rolling, and ancient ice is turning a knob you cannot see. Press play again. You will not hear the same minute twice. You will hear the same laws, alive,